Power system disturbances such as faults, line switching, or sudden load fluctuations can trigger power swings. If these swings become excessive, generators may lose synchronism with one another. To mitigate this, out-of-step protection was developed, enabling rapid detection and response to separate asynchronous areas. Advancements in OOS technology have improved detection accuracy and the coordination of protective measures, strengthening system security and reliability. The United States power grid has experienced several major disruptions, including the August 14, 2003 blackout and significant outages in 1996, affecting millions of users. These incidents typically occurred under heavily loaded conditions, where multiple outages happened in succession, causing oscillations, voltage drops, and instability in both voltage and phase angles. Since designing a system to fully prevent such rare simultaneous failures is extremely costly, utilities employ special protection systems and remedial action schemes, such as under-frequency and under-voltage load shedding, along with controlled tripping of loads or generation, to minimize disturbance impacts. OS protection for generators became a priority following historical blackouts, including the 1965 Northeast power failure and the 2003 blackout, prompting industry groups to develop guidelines for OS relay configurations. OS occurs when a generator loses synchronism with the system due to disturbances or automatic voltage regulator failures, leading to high peak currents, mechanical stress, and pulsating torques necessitating separation through OS tripping relays. If disturbances are mild, the generator stabilizes with oscillations in its load angle, while power swing blocking relays prevent unnecessary tripping during stable swings, ensuring unaffected generators and transmission lines remain operational. Under normal conditions, a generator maintains constant speed by balancing electrical and mechanical torque. However, if a fault reduces transmitted power, the electrical torque drops while mechanical torque remains, causing rotor acceleration. Consider a two-source power system at a balanced angle transferring power. Following a fault, power output declines to PF, leading to rotor acceleration and an increase in delta. Once the fault clears at delta C, higher electrical power output PC generates decelerating torque, but inertia keeps delta increasing until it reaches delta F, where gained acceleration energy equals lost deceleration energy, a condition described by the equal area criterion. If delta F remains below a limit delta L, the system stabilizes and returns to its original balance, but exceeding delta L leads to transient instability, where the rotor accelerates uncontrollably, causing a loss of synchronism. Power system stability refers to the ability to return to a stable operating condition following disturbances such as faults, load changes, or generator disconnections. System integrity is upheld if only faulty components are isolated while the remainder continues functioning. When generators or zones lose synchronism, immediate separation is essential to prevent widespread outages and equipment damage. A crucial mitigation strategy is controlled islanding, executed via two complementary OOS protection schemes. Out-of-step tripping OST targets specific network locations to disconnect unstable system areas, mitigating the risk of cascading failures. Out-of-step blocking OSB ensures that protective relays do not trip unnecessarily during stable power swings, keeping essential system components connected. The impact of a power system disturbance depends on both the system's initial operating state and the disturbance's severity. A fault in a critical area, once isolated, causes fluctuations in power flow, bus voltage, and generator rotor speeds, prompting responses from voltage regulators and speed governors. Depending on severity and protective system actions, the system may either stabilize or become transiently unstable. In an unstable scenario, significant variations in generator rotor angles emerge, accompanied by large fluctuations in power flow, voltage, and current. These disturbances can ultimately lead to generators or interconnected systems losing synchronism. When two power system areas fall out of sync, the entire network experiences extreme shifts wherein phase operation results in high voltages with low currents, whereas a 180-degree phase difference causes low voltages and high currents, leading to severe system instability. Out-of-step protection schemes address these conditions, ensuring distance relay performance remains effective under such circumstances. Key challenges include handling unbalanced external faults and ensuring that only the affected phase trips, rather than all phases, during a fault. Under normal steady-state conditions, all synchronous generators operate near their nominal frequency, balancing mechanical torque with electrical power output. If disturbed, differences in generator speeds cause shifts in rotor angles. Initially, the system self-corrects by redistributing loads among generators. However, excessive angular differences can reduce power transfer, potentially leading to sustained instability. Loss of synchronism affects transmission line relays differently. Some systems, such as segregated line differential relays, remain unresponsive to these events, while others including overcurrent, directional overcurrent, and distance relays may react to voltage, current, and phase angle changes. In some cases, relays may trip during stable power swings that the system could otherwise recover from. For example, instantaneous phase overcurrent relays trip if the line current exceeds their threshold during a swing. Directional instantaneous overcurrent relays activate if both current magnitude and phase relationships align. Time overcurrent relays generally remain inactive but may respond based on current levels and delay settings. Distance relays, which measure positive sequence impedance, are particularly sensitive to power swings. When an OOS event occurs, the impedance locus may enter the relay's operating region. Zone 1 elements, which operate without delay, are highly sensitive, while Zone 2 elements, used in pilot relaying schemes, are also prone to activation. Conversely, backup zones, due to their time delays, often remain unaffected by power swings. The operation of distance relays during swings depends on the interaction between the relay's polarizing memory and measured electrical parameters. Modern microprocessor-based distance relays, equipped with frequency tracking, are less influenced by memory rotation. However, if a line's positive sequence impedance is significantly higher than system impedance, relays may still trip unnecessarily. Some out-of-step tripping relays provide only tripping functionality, while others also integrate power swing blocking to prevent unwanted activations. Detecting an OOS condition typically involves analyzing apparent impedance at the generator terminals. Transient stability studies determine whether a generator can retain synchronism under various contingencies. During an OOS event, impedance shifts reflect voltage and angular differences. When system sources are in phase 0-degree angle difference, generator terminal voltage peaks while current remains low. In contrast, when fully out of phase 180 degrees apart, voltage drops to a minimum while current spikes. To distinguish OOS conditions from actual faults, protection devices analyze the rate of voltage, current, and impedance changes. Fault conditions cause near-instant impedance shifts within milliseconds. Power swings, however, evolve gradually. For example, a full 180-degree swing at 1 Hz takes approximately 0.5 seconds. Since both faults and power swings can cause impedance to enter the relay's activation range, precise tracking of impedance change rates is critical. Practical implementations employ impedance boundaries with timing mechanisms. If impedance remains between predefined limits for a set duration, an OOS condition is confirmed, blocking relay operations. Various boundary shapes such as double blinders or concentric polygons are positioned strategically to avoid false triggers. OOS protection serves two core functions. Tripping protection identifies unstable power swings and isolates affected network areas through sectionalizing or islanding strategies to maintain generation load balance. Blocking protection prevents relays from tripping during normal swings while ensuring proper operation during genuine faults. These protective schemes are typically deployed at critical network locations, such as electrical centers, with additional measures like transfer tripping schemes used for controlled separation. OOS tripping is carefully designed to avoid activation at near 180-degree phase angles, as this could impose excessive stress on circuit breakers. By minimizing cascading outages, limiting load loss, and ensuring system continuity, OOS protection helps safeguard equipment during both transient and unstable conditions. Turbine control mechanisms, such as power load unbalance protections, may engage during system disturbances or load rejection events but should not be confused with an OOS event. Overspeed often occurs after pole slipping, whereas an undetected OOS condition may eventually lead to overspeed. This underscores the importance of dedicated OOS protection relays. A crucial parameter for relay settings is the critical clearing angle delta C, marking the boundary between stable and unstable responses. While a common reference value is delta C 120 degrees, comprehensive stability studies help determine the actual threshold. These studies assess system behavior by progressively increasing fault clearing times until instability emerges, identifying the critical angle and associated swing rates. As power system oscillations unfold, relays measure impedance variations over time. Improper settings can lead to misoperations in protection elements. These impedance shifts can be represented using a simplified model of two generators, where receiving end voltage ER lags sending end voltage ES by angle delta S, influencing system stability. Two key stability concepts apply: small disturbance stability steady state, the ability to absorb minor load or configuration changes within 10 to 20 seconds. Transient stability large disturbances, the ability to maintain synchronism during severe disturbances typically over 3 to 5 seconds such as faults or sudden load fluctuations. A power system is stable if oscillations damp out over time. However, an unstable system experiences growing oscillations that ultimately lead to loss of synchronism. The relationship between sending end voltage ES, receiving end voltage ER, total reactance X, and phase angle delta governs power transfer. As delta increases, power transfer rises until 90 degrees, beyond which further increases reduce power flow. When faults occur on transmission lines, effective reactance changes due to additional shunt reactance XF introduced at fault points. Different fault types including single line to ground, line to line, and three-phase faults affect reactance differently. For instance, single line to ground faults cause smaller reactance variations. Three-phase faults can fully disrupt power transfer between generators. By strategically deploying OS protection and relay coordination, utilities can effectively mitigate power system instability, ensuring continued operation and preventing widespread outages. Out-of-step protection ensures power system stability by mitigating disturbances through out-of-step tripping and power swing blocking. The power angle curve helps visualize generator behavior, highlighting how power transfer peaks at 90 degrees and instability risks increase beyond 120 degrees. Impedance shifts occur suddenly during faults and more gradually during power swings, requiring distance relays to differentiate between the two. Transient stability depends on maintaining rotor angle within safe limits. Exceeding the critical clearing angle delta C can lead to loss of synchronism and generator separation. Protective measures like PSB relays prevent unnecessary tripping, while advanced detection strategies including graphical methods, impedance rate tracking, and PMU-based monitoring help distinguish faults from power swings. OST actively disconnects unstable areas, while OSB prevents relays from misinterpreting stable oscillations as faults. Properly configuring relay timing, adaptive settings, and strategic islanding enhances grid reliability, reducing cascading outages and equipment stress. The implementation of out-of-step tripping and power swing blocking plays a vital role in maintaining power system stability by preventing cascading failures and ensuring controlled isolation of unstable areas. OST disconnects generators or network segments that have lost synchronism, while OSB prevents unnecessary relay activations during stable power swings. These functions are strategically deployed at key network locations and dynamically adapted to changing system conditions, including load variations and renewable energy integration. Modern innovations such as phasor measurement units (PMUs), adaptive relay settings, and impedance-based detection algorithms enhance fault differentiation and improve protection coordination. Effective implementation requires extensive transient stability analysis, precise relay timing, and optimized rate of change monitoring to ensure reliable operation. By combining strategic islanding, real-time monitoring, and advanced fault detection, utilities can strengthen grid resilience and minimize system disruptions during power swings and fault scenarios.